This is problem set number 6, problem 5. A long coaxial cable consists of an inner cylindrical conductor with radius A and an outer coaxial cylinder with inner radius B and outer radius C. The outer cylinder is mounted on insulating supports and has no net charge. The inner cylinder has a uniform positive charge per unit length L, and we want to calculate the electric field. Okay, so we have two cylinders, an inner cylinder right here with radius A, and an outer cylinder that's hollow on the inside with an inner surface radius of B and outer surface radius of C. Okay, so that's the second cylinder enclosing around inner cylinder with radius A. Another thing that's given is that the outer cylinder is on insulating supports and it has no net charge. Then the inner cylinder has a uniform positive charge per unit length L. Or in other words, it has a uniform charge density, lambda. Okay? So part A, calculate the electric field at any point between the cylinders, a distance r from the axis. So if we want to calculate the electric field here, right, between the cylinders, then our radius would have to be between radius A and radius B, okay, to get here, or the space between the two cylinders, okay? And so I did that here. I've drawn that in this diagram here. So we want to get here between radius A and radius B, right? I want to find the electric field here. And in order to do that, I've drawn a Gaussian surface with radius r, okay? So that's my Gaussian surface with radius r. And radius r again is between radius A and radius B. So it's somewhere here in this region. Okay? To solve for the electric field, I'm going to use this formula, the electric flux formula, which is the surface integral of the electric field of our Gaussian surface times dA, which is also equal to the charge enclosed, Q enclosed, over the permittivity of free space, which is a constant epsilon naught. Okay? So when we look at our Gaussian surface, right, we want to look at the electric field. One of the useful Gaussian surfaces that we use in chapter 22 is the cylinder, okay? And as you can see, there's an electric field here and here from the cylinder, right? Because of this positive lambda charge of the inner cylinder that this inner radius, or this Gaussian surface encompasses, right? So because of this part of the inner cylinder that's encompassed by the Gaussian surface, there's a certain electric field that it feels right here, okay? So the other thing is that we have this surface for the cylinder that's smooth, the sides, right? And these have normal vectors pointing there and pointing there, radially. Or sorry, around the cylinder right here on the sides, right? And then we also have the vector normals from the flat surfaces right here, right? And we notice that the angle between this normal vector and the electric field is 90 degrees, right? Can you guys see that? Like if this angle is 90 degrees, right? So is this angle. That's also 90 degrees. So as a result of that, our electric field for these two surfaces is going to be 0. Whenever the angle between the the normal vector and the electric field vector is 90 degrees, then the value of the electric field is 0 for that, okay? But when it's perpendicular, like on the side of the cylinder, or sorry, when it's parallel, like on the side of the cylinder for this normal vector and electric field and this normal vector and this electric field, then we have a value for that, okay? That's a constant. So we can actually take this electric field out of this surface integral like I did here and just treat it like a constant, okay? So we're gonna do that. And so we've taken this out, this electric field out because it's a constant, right? Now the surface integral of dA, that's just going to be the surface area of my Gaussian surface, which is a cylinder right here, right? And if I go ahead and I'm going to give you guys the surface area formula for a cylinder, okay? So surface area for a cylinder is equal to 2 pi r squared. And that pi r squared right here is for the flat surfaces. So you've got one flat surface here and another flat surface there, right? So that's why 2 pi r squared, that's a surface area, or that's basically the area of a circle, right? And we have 2 of those flat surfaces, so that's the 2 right there. And then plus the surface area for this side of the cylinder, okay? Which is going to be 2 pi r times the length of the cylinder, okay? So I want to state that this is the surface area for the 2 circular flat faces. Okay, that's for this side and this flat face on the other side right here. And then this 2 pi RL, that's for this guy, the side of the cylinder, okay? Or we'll call that the non-flat side. Non-flat face of the cylinder. Just wanted to clarify that, okay? So if you guys don't have this formula for the surface area of a cylinder in your cheat sheet, I highly recommend to have that, okay? Again, that's what we will plug in for our dA right here, okay? That's just going to become the surface integral of dA. That's just going to be the surface area of a cylinder. But because the normal vector for the 2 circular flat faces is perpendicular with the electric field, I'm going to ignore that. It's going to be, the electric field for that is 0, right? So I'm going to ignore that. I'm going to focus on where the electric field is here, a constant, which is going to be when my normal vector is parallel to the electric field vector for these guys, okay? Okay. So times 2 pi, my radius for the Gaussian surface is r, and my length for the Gaussian surface is L, okay? And for Q enclosed, right here, I'm going to go back to where they said that my inner cylinder has a uniform positive charge per unit length L. Okay, so it has a uniform positive charge per unit length L, or a uniform charge density. So that's what I've drawn here. And if I want to find my Q enclosed, right, that's going to be the charge that's enclosed. I'll use green within this part of the inner cylinder, right? And the reason there's a charge there is because this inner cylinder has a uniform charge density of Q over L, Q over length L, or lambda, right? So to find Q enclosed, I multiply my charge density by the length, and I'm just going to substitute that here. Instead of Q enclosed, I'm going to say lambda L, right? Because that is that's a charge density that's enclosed within length L right here, okay? And over epsilon naught, okay? So if I find the electric field for part A, that's going to be equal to pi L over 2 pi R L epsilon naught, right? And my L's are going to cancel out. So I'm left with the electric field is equal to lambda over 2 pi R epsilon naught. That's my final answer. That's the electric field for my radius when my distance between A and B, between radius A and radius B. Okay. And if you guys want to know the direction as well, the electric field points radially outward since the inner cylinder does have a positive charge, positive Q over L, right? So, yes. All right, moving on to part B. Part B, we want to calculate the electric field at any point outside of the outer cylinder. So part B is going to be the electric field at any point outside the outer cylinder. Okay? So that's when my R is going to be greater than radius C. Because my outer cylinder has an outer radius of radius C. So I'm going to plug that in. Okay. So I'm going to I want to find the electric field outside here, outside my outer cylinder. So my radius for that electric field will have to be a R, right? A distance R. So that's going to be the radius, which is going to be greater than C because C goes until here, right? Okay. So I'm going to draw another cylinder. I'm not the best artist. It's a bad looking cylinder. All right, anyways, that's a cylinder, right? This is the flat surface. So that cylinder has a radius of R, and R is going to be greater than C. All right, and I'll also give it a unit length L. Okay. And the same thing as part 1, I'm going to use this formula to find my electric field. And that is the formula for electric flux, right? Okay. So same things. I'm going to have electric fields that will be coming out this way because of this this charged inner cylinder, right? And then I'm going to have my normal vector normals for my Gaussian surface. And like I said, I'm just going to worry about my my surfaces, same as in part A, right? What we talked about in part A. I'm just going to worry about the surfaces that have parallel normal vectors with my electric field, okay? With my electric field vectors. And that's going to be this side face, not the flat faces where the vector normal and the electric field vector have an angle of 90 degrees between them, right? When they're perpendicular, that's electric field is 0, so I'm not going to worry about that. Okay, so same thing as in part A. My electric field is constant, so I'm going to take it out of the surface integral, and I've got to get the surface integral of dA, which is equal to Q enclosed over epsilon naught. Okay. And the Gaussian surface area for, or my Gaussian surface area for a cylinder is going to be this 2 pi r, right? Sorry, that's supposed to be 2 pi. I forgot the L. 2 pi RL. That's not even the complete Gaussian surface area. Sorry. Okay, so my Gaussian surface area is right here, right? The surface area of a cylinder. Again, I'm going to ignore this two circular flat faces term because electric field is 0 when the normal vector is perpendicular with electric field. So I'm just going to focus on this term, the non-flat face of the cylinder, which is here, the side of the cylinder, because my normal vector is, for my Gaussian surface, is parallel with the electric field, right? Okay, so my surface area is going to be, it's going to be E times my Gaussian surface area of 2 pi r, and my length is that unit length L, right? And that's going to be equal to the charge enclosed, which is still this guy, that charge for the inner radius, because the inner radius has a charge density of positive Q over L, right? Positive lambda or positive Q per length, right? So I'll call that positive lambda, positive charge density lambda. Okay. I'm not going to repeat the process, but as we can see with positive charge density lambda, we've got positive charge Q enclosed divided by L, right? The charge enclosed here divided by L. So I'm going to say my Q enclosed is equal to lambda times L, okay? So that's equal to lambda times L divided by epsilon naught. And if I look for the electric field there, that's going to be equal to lambda over L divided by epsilon naught, 2 pi RL. Okay, and we'll cancel out the L's. So our electric field at any point outside of the outer cylinder when the distance r is greater than c is equal to lambda over epsilon naught 2 pi r. Okay? And that's the final answer for part B. Again, the electric field is going to point radially outwards, right? So out here, out there, out of the page or out of the screen, and into the screen, right? Everywhere. It's like everywhere normal to this surface. Okay? Because the inner cylinder has that positive charge. Okay, so now let's move on to part C. So for part C, we're going to graph the magnitude of the electric field as a function of the distance r from the axis of the cable from r equals 0 to r equals 2c. Okay? So we're going to graph basically the electric field, the magnitude of electric field, as a function of r, which is our radius for a Gaussian cylinder, right? Our Gaussian surface. From the axis of the cable, so we're going to go from, I said, go from 0 to A to B to C and all the way to 2C, right? Until 2C, which is just the area outside of the outer cylinder, which we calculated the electric field for here, right? In part B. Okay, so I'm going to do that. So recall that in chapter 22, section 5, we talked about the electric field inside conductors and that they're always 0, right? So any charges in the conductors are going to have to reside in the surfaces, right? On the surface. What I mean by that is if I have a conductor right here, and this conductor has uniform positive charges, right? Those charges are going to reside on the surface of the conductor. Okay? But the electric field inside the conductor is always 0. Okay? And that we talked about in chapter 22, section 5. Okay? So let's think of our electric fields, right? When r is less than a, we're going to reside here, inside this inner cylinder, right? And we talked about, or it was given to us that the inner cylinder, is a conductor with radius a, right? So it's a conductor. So because it's a conductor, then the electric field inside that conductor, when r is less than a, is equal to 0. Okay? Electric field is equal to 0. All right? And when r is going to be greater than a but less than b, so this time when you reside here in the area between the two cylinders, right? That's going to be the electric field we calculated in part A, which was when r was between a and b. And this was our electric field for that, right? So I'll write that down. When r is greater than A but less than B, the electric field is lambda over 2 pi epsilon naught times R. Okay? What about when the radius is less than, or is greater than B but less than C? Or in other words, here in this area, or here inside our outer cylinder, right? Remember that the outer cylinder has no net charge enclosed, right? So if the outer cylinder has no net charge enclosed, so if this guy on the outer cylinder has no net charge enclosed inside it, so charge enclosed, actually I'll bring that formula down. If the charge enclosed was 0, right? Since the electric field has to be constant in our Gaussian surface for a cylinder, right? When it encompasses this outer cylinder. If the charge enclosed, if the electric field is constant, then it also has to be 0 if the charge enclosed is 0, which it is. There's no net charge for the outer cylinder, right? So because of that, the electric field has to be 0 as well. Here. All right, what about when R is greater than C? We solved for that here, right? That was when we looked for the electric field at any point outside the outer cylinder. Anytime you're outside the outer cylinder, R is going to be greater than C, right? So any 2C, that's greater than C, and that's also outside the outer cylinder. And we know here the value for electric field there. And that is lambda over 2 pi epsilon naught R, right? And you see here these two values for electric field are equal. Right? And they're both an inverse, right? 1 over some constant over R. So if we're going to graph that, that's going to look like sometimes this straight line thing works. Sometimes it doesn't. Whatever. Okay. So that's going to be radius R, a graph of electric field as a function of the radius, right? Or as a function of the distance R. And we've got our values for electric field right here. Oops. So when, let's put our values for radius. So we have when radius is 0, right? When radius is A, when radius is B, when radius is C, and then anything greater than C, when R is greater than C, right? We know that the value when R is less than A, the electric field is 0. We also know that the electric field is 0 when the distance r is between B and C, between radius B and radius C, right? But we do know that at a certain distance, when r is between radius A and radius B, and when distance r is greater than radius C, we have a certain value for our electric field, right? And that's just going to be an inverse function, so I'll have a certain value there, inverse. So that will be, okay. And that is the graph for part C. That's going to be the final answer for part C. Right, this is any constant 1 over r, or 1 over r. I mean, we can not really think of that constant, right? It doesn't matter. It's going to be some 1 over r kind of graph, or 1 over x, depending on what your value is. What your variable is here, but in this case we have r. Okay. Now this thing's not working. There you go. Okay, now for part D. All right. Find the charge per unit length on the inner surface and on the outer surface of the outer cylinder. So find the charge per unit length on the inner surface and also on the outer surface of the cylinder. All right, so let's start with the inner surface. Looks kind of sloppy. So for the inner surface, right, I'm going to do a cross-sectional view of our cables. So I have a certain inner cable right there. I have an outer cable. Okay. And then I also have my outer cylinder also has an outer surface. Okay. So my inner cylinder has radius A. So this has radius A. The inner surface of my outer cable is radius B. And the distance to the outer surface of my outer cylinder is radius C. Okay? And my inner radius, let's use orange. My inner radius here has a certain positive lambda surface charge, right? Or charge of positive lambda L, right? We solved for that earlier, right? Surface charge is lambda L, okay? And then my inner surface goes until radius B right here, right? So if I want to find the charge per unit length on the inner surface, I'm going to draw a Gaussian surface that's bigger than my inner surface, but smaller than my outer surface of my outer cylinder, okay? Okay. So we figured out from part C, right, in our graph, that the electric field between radius B and radius C is 0. So with that knowledge, I'm going to use the surface, the electrical flux formula, which is equal to the surface integral of electric field times dA, or also equal to charge enclosed, Q enclosed over constant epsilon naught, right? And because I know that my electric field here between radius B and radius C is 0, here in part C, we calculated that, right? So this is going to be 0. So 0 is equal to Q enclosed over epsilon naught. Therefore, Q enclosed, my charge enclosed, has to equal 0 too, right? So in order for my charge enclosed to equal 0, when the surface is enclosed, my Gaussian surface is enclosed on the inner conductor right here with a charge of plus lambda L, then that means that the inner surface right here of the outer conductor is going to have to, it's going to have a charge of minus lambda L, or then the opposite sign but equivalent magnitude of whatever charge is inside here, right? So my inner surface of the outer cylinder will have a charge of negative lambda L. To neutralize it, this positive lambda L inside, and neutralize it so that the charge enclosed here, charge enclosed is equal to 0, enclosed here in my Gaussian surface, okay? So that means, therefore, the charge per unit length on the inner surface of the outer cylinder is going to be negative lambda right there, right? That's a charge per unit length. Charge per unit length on inner surface of outer cylinder is negative lambda, okay? Which is equal to negative Q over surface area L, okay? Or surface negative Q over unit length L. So that's our final answer. All right. Now, we also have to find the charge per unit length on the outer surface of the outer cylinder, okay? So I'm going to draw that this time again. So for the outer cylinder, it's going to look like this. okay? And my outer cylinder will have this cross section where you see the green stripes, right? And then this inner cylinder right here, that's going to have a charge of plus lambda L, okay? And so if I want to find the charge per unit length on the outer surface of the outer cylinder, I just have to remember that the problem stated that the outer cylinder carries no net charge, right? And then we determined in this part that the inner surface of the outer cylinder has a charge per unit length of negative lambda, right? Or a charge per unit length of negative lambda, right? And it has a charge of negative lambda times the unit length L. So therefore, for the outer cylinder, the charge per unit length, again, this inner surface has a negative lambda charge per unit length, right? And the problem states that there's no net charge on the outer cylinder. So in order for there to be no net charge and to neutralize this negative lambda on the outer cylinder, the outer surface will have a positive lambda charge per unit length, right? So that they neutralize each other and cancel each other out so that there's no net charge on the outer cylinder. So therefore, the charge per unit length on the outer surface of the outer cylinder, or the charge per unit length on outer surface of outer cylinder is positive lambda. Okay, that's our final answer.